I'm Ryo Hirai. I'm a postdoc at Monash, and I would like to talk about pulsar rockets. Um, so you may know that neutron stars are known to be born with high spatial velocities. The typical observed velocities range from about 100 to 1,000 kilometers per second, with the distribution peaking around 300 kilometers per second. So these are very fast velocities compared to all the other stars in our galaxy. Now, these are called neutron star kicks. So there's many mechanisms that have been proposed to explain why neutron stars are born with these high spatial velocities. And the mainstream mechanisms are related to the mechanism of core collapse supernovae that give birth to the neutron stars. So you may know that core collapse supernovae require a very turbulent asymmetric accretion onto the protoneutron star, and also this emission of neutrinos to drive the explosion. And if there's any small asymmetry in the ejected material from the core, this could lead to some recoil to the neutron star that will accelerate it to these high velocities. Also, there's a huge amount of momentum reservoir in the emitted neutrinos. So again, if you have the tiniest bit of asymmetry in the neutrino emission from the protoneutron star, that could also give some recoil to the neutron star and drive it to those 100 kilometers per second speeds. But the important thing is this is related to the core collapse mechanism, which occurs on a dynamical timescale of the core, which is of the order of about a second or maybe about 10 seconds, which is extremely short. However, in the past, there have been mechanisms that have been proposed which don't occur on the core collapse timescale, but rather the spin down timescale. So, for example, in this Harrison and Tadamaru model, if the magnetic field is offset from the center of the neutron star by a bit, and if the spin axis is misaligned with that, the spin down luminosity would be very asymmetric. You have a stronger flux going in one direction than the other. And that could lead to a net acceleration of the neutron star. And in fact, these off-centered fields are sort of supported by the nice observations of hotspots on the surface of neutron stars. There's also another mechanism called the neutrino rocket mechanism, where the cooling neutron star cooling through neutrinos will lead to an acceleration, because they claim that the emitted neutrinos would be aligned with the superfluid vortices, which would in turn are aligned with the neutron star spin. So these occur on the spin down timescale, which is typically of the order of years to centuries. So this is completely different from the 1 second timescale that we used to when we're talking about neutron star kicks. This is mostly important when you put it in binaries, because in the grand scheme of things, 100 years is still very short in astronomical terms. But when you look at the binary orbits of binaries containing neutron stars, they're typically the orbital periods are typically less than a year. So if your acceleration timescale is longer or comparable to or longer than a year, we can't make this instantaneous approximation anymore, and therefore the orbit of the orbital evolution would be completely different. So my study is to explore what happens if the kick is not instantaneous, but instead on a longer timescale than the binary orbital period. Now, neutron star kicks are crucial in terms of massive binary evolution because it determines the fate of the binary, whether it can survive as a binary. For example, if you take any typical binary evolution paper, they would show a diagram like this. And if you have a supernova in a binary, most of the time you will actually just disrupt the system, because the kick is so strong. 95% of the time you would disrupt the binary. Also, even if you do survive, it will induce a high eccentricity to the orbit, and this is sort of seen in some of these double neutron star observations. If you're very lucky, if you point the kick directly at your companion, you can cause some collisions like you see in this movie, which also leads to very interesting phenomena. But again, all these typical traditional binary evolution scenarios assume that the kick is instantaneous, but again, if any of these rocket mechanisms come into play, all of these traditional mechanisms kind of fall apart. So I derived the analytic solution for the two-body problem when you have a constant acceleration on one of the bodies. This is sometimes called the accelerated Kepler problem or a classical Stark problem, which is actually has been studied in real rocket science where you want to place satellites into orbit and things. But the equation of motion is extremely simple. You just have gravity from both objects, and you have acceleration on one of the bodies. And we also want to make the approximation that we can make the secular approximation where the acceleration is much longer than the orbital period. Therefore, we can take orbit averages. Now, the existence of an analytic solution has been proved in the 70s, but nobody really derived a simple enough form for the analytic solution. I came up with this like new vector where I just simply take the sum and the difference of the dimensionless angular momentum vector and the Runge length vector. And then when I write down the equations using these vectors, it turns out that it's this really simple ordinary differential equation form. So you can actually integrate this by hand, and this is the solution. So basically what happens is you have this H plus and H minus vector that describes the orbit of the binary. And then if you accelerate it with the rocket, these vectors just rotate around the direction of the acceleration. And then if you know the total amount of thrust that was given from the rocket, you know your post-supernova orbit based on these two vectors. You can reconstruct the Runge length vector and the orbital angular momentum from that. So to verify this analytic solution, we did some numerical experiments of just simply integrating the two-body problem. And you can see what happens is that the eccentricity of the orbit just goes up and down based on how much you accelerate the neutron star. At the same time, the orbit rocks around, changing the direction. And in the end, once the acceleration ceases, you should stop somewhere along this curve. And the maximum, well, the amount of eccentricity oscillation depends only on the initial eccentricity and the direction of the rocket. So for example, if you start with a circular orbit and your rocket's aligned with the orbital angular momentum, it doesn't do anything actually. It just pulls the companion up. But so you need some sort of tilt or initial eccentricity. But this is always naturally provided if you have a supernova. So if you have a supernova, you always have some amount of mass loss in the supernova ejector, which leads to an effective kick, which we sometimes call the Blau kick, which will induce some eccentricity. And also, there's no reason why the hydrodynamical instantaneous kicks don't act if you have a rocket. These two things are not mutually exclusive. So you would always have two effects already inducing some eccentricity and some tilt to the rocket direction. And then on top of that, you can add some rocket on it. So here's an example of how the orbit evolves with all three components considered. So we're starting off with an orbital period, we just normalize, so it's here, 1, and we're starting with a circular binary. And the mass loss will take you up to some eccentricity and some wide orbital period. And then the usual rapid kick, so the usual natal kick, will usually change the eccentricity in a way, in a very correlated way along this red strip. This is just traditional binary evolution theory. But then if you add a rocket on top of this, you can then spread out the eccentricity distribution vertically. So the rockets will not change the orbital period, but just simply vertically oscillates the eccentricity. And the colors just are the different colors based on just different constraints on the rocket direction. But basically what it does is, yeah, you get different eccentricities from the same system. Now, why this is interesting is, well, this is interesting, and particularly if you look at the periastron distance after the supernova. So in the traditional natal kicks, so the instantaneous kicks, if you look at the periastron distance after the supernova, most cases, so if you look at the blue stuff, the blue dots, most cases you don't really change the periastron distance. You just like widen the orbit. The pre-supernova orbital separation is your post-supernova periastron distance. Only if you kick it in a really nice direction, you can sometimes shrink the orbit or the periastron a bit, but not too much. Obviously, this depends on the strength of the kick as well. But even if you apply the same amount of kick, but in the form of a rocket, you can actually go a bit deeper. So the red line shows the post-supernova orbit if you have a pure rocket-like kick. And then, but the most interesting stuff happens when you have a mixture. So I then made a model where you have half rocket and half natal kick. And that is the green stuff, where you can see in the extreme cases, the periastron distance goes all the way to 0, which means after the supernova, you can actually directly cause a head-on collision of the binary, which isn't possible, most cases not possible with normal natal kicks. So this has huge, well, really nice implications astrophysically. For example, first, if you replace half of the known kick distribution with rocket-like kicks, that means you would expect a higher fraction of surviving binaries, simply because the rockets don't really change the orbital period. Because you get tight periastron distances, it could aid the formation of X-ray binaries, low mass, high mass, B X-ray binaries, and also double neutron star systems. Also could accelerate the merger timescale because they have a shorter periastron. But the other thing is the eccentricity oscillation doesn't always happen in an increasing direction, but also could decrease. So there's a way to make very wide but circular orbits with binaries containing neutron stars, which is actually quite difficult in normal scenarios. There's also even more interesting stuff if you put the rocket in a triple system, which I'm still working on. So if you have a rocket in a binary, that thing, the eccentricity oscillates and things, but at the same time, you're also accelerating the system as a whole. So if you have a tertiary system far away and a hierarchical triple, this whole binary, the inner binary, is a rocket on its own in a binary with the triple, the tertiary star. So there's going to be like 2 different oscillations going on in and out, which I thought could be described by my analytical solution, but it turns out that the inner binary has some extra effect from from other secular triple effects, which I don't really understand yet. But this, I'm thinking, could be a new channel to explain the formation of this very weird gravitational wave event called GW 190814. But this is still preliminary work, so please, let's discuss if you have any interesting ideas. So I'll put in my summary. Thank you for listening.
Thanks. That was really nice work. I was wondering, you started your talk by showing the period distributions of neutron star binaries.
Yep.
Did you ever come to looking at these distributions and seeing whether they tell you something about the presence of this mechanism?
Yeah, so, well, actually, this project started off trying to explain this seemingly bimodal eccentricity distribution of double neutron stars. So, yeah, this very puzzling bimodal distribution. My thought was, if you have a Blau kick, so if you try to explain this with traditional kicks, to get here, your pre-supernova orbit has to be here, because you can only spread it out this way. But if you have a rocket, you can take it from here to here. So having a binary here, which is like an less than an hour orbital period, is quite challenging in traditional binary evolution. But taking it from here to here is kind of easy. So I thought, yeah, I could explain these, but also the bimodality, because if the Blau kick takes you here, and then the oscillation takes you one way or another, so it kind of spreads it out in this direction. And actually, under some assumptions, I could make the bimodal distribution. Yeah, thanks.
Yeah, really interesting work. I'm wondering what are the magnitudes you would expect for the kicks you receive from such a rocket mechanism? I'm just asking because we find with pure hydro and neutrino kicks on the order of over 1,000 kilometers per second in the most extreme cases. So do you think a rocket is really necessary to explain magnitudes of observed kicks?
I don't think it's necessary to explain the magnitudes. I mean, hydro kicks are pretty much enough to explain the distribution, but there's no reason why it shouldn't be a rocket. Especially after the nicer observations, it looks like the magnetic fields are actually offset, and based on their models, if the field is offset that much, you would naturally expect asymmetric spin down luminosity. So this strongly depends on the initial spin distribution of the neutron stars. So if you have an initially millisecond pulsar, that would lead to 1,000. But if it's initially 10 milliseconds or less, it's of the order of 100 or less.